Hello, my name is Mario Hudon. I am a senior software engineer at INTERDIGITAL. I am specialized in embedded systems and real-time software development. For the past 3 years, I've been mostly working on 5G and R Layer 2 software implementation. In this presentation, I'd like to talk about 5G and R beam management functionality and its implementation status in the OAI stack. So, about a year ago, a NRFR2 collaboration between INTERDIGITAL and EURECOM has been initiated. INTERDIGITAL provided millimeter wave masthead units to support an integration effort between the OAI stack and an FR2 commercial off-the-shelf phone. This integration effort is still ongoing as we speak, and we'll come back to that a little bit later. In parallel to this MHU OAI integration work, 5G and R beam management feature is being implemented in the OAI stack through a joint effort between EURECOM, Global Edge Soft, INTERDIGITAL, and TCL. This includes both GNB and UE feature development, and the team is meeting every 2 weeks to discuss the development progress and any issues that we could have. So what is beam management? So beam management can be seen as a series of operations that establish and maintain a transmit-receive beam pair between the UE and the GNB to provide a better connectivity. So the first operation is the initial beam pair establishment, which is performed during the RATCH procedure. Then you have the beam refinement and switching to compensate UE movements and gradual changes in the environment. Also, there is the beam failure detection and recovery to handle a disruption of the current UE GNB beam pair. In the interest of time, we will just cover initial beam pair establishment and the beam switching, which are the two features currently being implemented in the OAI stack. There are many details to each operation, but I'll just do an overview to help understand the work accomplished so far. So let's start with initial beam pair establishment. First step of initial beam pair establishment is the initial beam selection itself. The GNB is following a pre-configured schedule to transmit the SSB's blocks on different beams. The mapping of the beams to the SSBs is determined by the SSB positions and burst RRC information element. In this example, a beam is mapped to every fourth SSB. Let's go with an example and start at frame 0. UE listen on its own beam 0 for SSBs sent by the GNB and records the beam measurements. So GNB sends SSB 0 over beam 0, then SSB 4 over beam 1, SSB 8 over beam 2, and so on until the end of the SSB schedule in the frame. 2 frames later, the UE listens on its next beam, and the GNB goes through its SSB's transmission sequence again. And so on until the UE has gone through all of its beams. While the GNB continues transmitting its SSBs every 2 frames, the UE is now in a position to select the best beam pair, which, let's say, that in this case is GNB beam 14 and UE beam 1. The second important step is the mapping of the SSBs to the RATCH occasions. Both the UE and the GNB are given a RATCH occasions schedule via the IE PRATCH configuration index. That index will ultimately define the schedule of the RATCH occasions in the time domain. A second IE, message 1 FDM, will define the RATCH occasion scheduling in the frequency domain. In this case, 2 ROs are multiplexed in frequency in every possible RO time location. Finally, a combination of the SSB positions in burst and the SSB per RATCH occasion information elements will allow to map each transmitted SSB to a specific RATCH occasions following an extensive set of rules that won't be covered here. The last step of the initial beam pair establishment is the UE RATCH preamble transmission on the proper RO and the GNB RO beam detection. Here's how it works. So the initial beam pair has been selected by the UE in the first step. UE knows that GNODE Beam 14 is associated to SSB-56. With the SSB-56 mapped to RACH occasion 14, UE needs to use this RO14 for the RACH preamble transmission. UE uses its RO schedule to determine when to send the RACH preamble in time and in frequency. And the RACH preamble is sent over UE Beam 1 at RACH occasion 14. GNODE B detects the RACH preamble at RO14 and does the reverse logic to determine that the random access response should be sent over Beam 14. And the initial beam pair is established. Here's the initial beam pair establishment implementation status as of today. RACH occasions and SSB configuration and mapping is done on both UE and GNODE B. Proper RACH occasion transmission and identification in the RACH procedure is done, as well as the route transmission on the proper beam. PRACH for FR2 is also implemented and tested with PRACH Sim. Basically, most of the work left to do is at the file layer, where the initial beam selection, the first step that we talked about, still needs to be completed, as well as the physical beam selection, according to the information provided by the MAC layer. And now on to beam switching. Beam switching is made of two major steps: beam measurements and reporting, and the beam switching itself. The UE is configured to report GNODE B beam measurements via the CSI report config information element. In the current implementation, beam measurements are based on the SSBs and are reported periodically. In this example, the initial best beams combination is GNODE B Beam 4 and UE Beam 3. The procedures to take beam measurements is basically the same as what we've seen in the initial beam selection. The UE takes GNODE B beam measurements, looping through all its own UE beams and report the best GNODE B beam to the GNODE B. And as the UE rotates and moves, it eventually detects that the best GNODE B is now beam 3. A beam switch will be necessary. So how's the beam switch actually made? Well, the GNODE B schedules the reception of the periodic beam measurements provided by the UE in an uplink control information over PUCCH. The GNODE B extracts the measurement report of a target beam transmitted over PUCCH and compare the RSRP measurement of the target beam to the current beam. Assuming that beam 3 is the new best GNODE B beam, the GNODE B sends a PDCCH TCI state indication in a MAC control element over the PDSCH. The UE acknowledges the reception of the MAC PDU, and the new PDCCH beam will be selected according to the requested TCI state by both the UE and the GNODE B 3 subframes plus 1 slot later. Using the new selected beam for the PDCCH channel, the GNODE B either sends a DCI-11 with TCI info or a DCI-10 with no TCI. This depends on the information element TCI present in DCI. The UE will switch to the PDSCH beam based on either the TCI state in DCI-11 or reuse the one previously sent in the MAC CE, and the beam switching is completed. The current status of the beam switching implementation looks like this. All the RLC configuration items are partially developed or ready to be tested. For the measurements, handling of CSI measurement based on SSB is completed on the UE, but needs more testing on the GNODE B. CSI-RS is still to be developed and tested. For the beam switching part, handling of the TCI states is under development on both the UE and the GNODE B, but the construction of the MAC CE related to TCI states is done on the GNODE B. Beam switching using CSI-RS measurements is still to be developed. So what is the status of the beam management tests? Sub-6 beam management testing is actually ongoing. First, an initial beam pair establishment has been validated between the OAI GNODE B and a CUTS UE in FR1. Random access configuration index 98 has been used for this particular test. Also, using the RF simulator, the full RATCH procedure has been tested between the OAI GNB and the OAI UE with hard-coded beam indexes. This allowed to validate the SSB-RO mapping table and make sure that the proper beam indexes were selected. For beam management millimeter wave testing, a test setup with OAI GNB and OAI UE and National Instrument USRP N310 and INTERDIGITAL MHU is used. GPIOs from the N310 are controlling the beam selection and the TXRX direction on the MHU. Two scenarios are currently being tested. The first one is a OAI GNB MHU setup trying to connect to a Samsung S10 in non-standalone mode. So far, the CUTS UE does not seem to see the 5G cell, and troubleshooting is ongoing as we speak. The second scenario is using OAI GNB and OAI UE in PHY test mode. In this case, the RATCH procedure has been bypassed for these tests. Some downlink traffic has been established, but with very poor throughput, while real-time issues are observed on the OAI UE. So as you can see, there is still a lot of work to do. So if anybody would like to contribute to the development effort, I'd invite you to contact Florian and the EURECOM team. If you have any question, the beam management development team is online to answer them. Thank you.